Hello, everyone. Welcome to the second advanced track meeting. Today, we'll be talking more about CNNs. So we'll discuss some CNN architectures, and then we'll show you guys some guided scouting code that we will walk you guys through. But before we get started on the new material, we'll just do a quick review of the old material, and then we'll also discuss optimizers a bit, because we thought like it would be important to give you guys a look into how optimizers work when you guys are actually building your models in like stuff like our sample project, and then like later, and then future projects that you do later on down the line. So with quick review. So last week we introduced the concept of feed-forward neural networks, where you take an input layer, multiply it by a weight matrix, add a bias to it, and then pump that thing through a nonlinearity function so that you end up with more complexity as you add more layers. So in addition to this feed-forward format, what you also have is something called a loss function, which is a way that you describe essentially the score of how good your model is. And using this loss function, we can then take the derivative of the loss function to find the gradient of our model parameters. And that tells you how we should adjust all our model parameters, all the weights and biases, and how we need to make little tiny changes to them so that we can improve the model on the next round of feeding forward the next round of data. So that's the process of gradient descent, and that's basically what we covered for FFNNs last time. Next up, we talked about convolutions and filters. So this was as we started talking about convolutional neural networks, and what we talked about was essentially where you take a filter, as shown in this with this little orange square right here. And as you can see, the filter is running over through the image, and you're taking the dot product of the values of the filter and the values of the image, and that dot product gives you what the value goes in the these squares. And the values that you see inside the filter, which in this case are 101, 010, 101, those values are going to be learned by our model as it sort of does the process of gradient descent with our training data. And then lastly, we talked about pooling layers. And this is where you sort of simplify your image so that you end up with the most salient features of each part of it. And what you're doing here is essentially you're taking little chunks of your image, and you're going to pool together the values, either by taking the maximum value as shown here, or you can like take the average of the values inside as shown here. Generally, max pooling is going to be more common. It's going to be the thing that you'll end up using. But yeah, so we have, for convolutional neural networks, we talked about convolutions, and we talked about pooling. And you'll want to hang on to those concepts because we're really going to run with those concepts today. And we're going to build on them really like a lot. So does anyone have any questions about either what a convolution is, what a filter is, or what a pooling layer is? All good? Okay. Now we'll talk about optimizers. So first off, you might be wondering, why do we care about the kind of optimizer that we're using, right? The main thing is that with gradient descent, we know what steps we need to take in order to update our model. So we just like do simple gradient descent, and then we'll end up taking these steps we need to optimize our model performance. But the problem is that different optimizers are going to take these steps in different ways. And actually, there are better ways to take these steps and worse ways to take these steps. So the basic sort of just calculate the gradient and then take a step in relation to that and the learning rate, that's the very basics of it. But optimizers can be more sophisticated than that, so that we can get better performance out of them and get to the optimal results faster, or to even get more optimal results. So as you can see, this is sort of a visual demonstration of the fact that I just said, that you see this atom optimizer is doing way, way, way better than this optimizer up here. And all of these will presumably be doing better than the standard kind of optimization process that we talked about last. So we're going to be talking about Adagrad. We're going to be talking about not SGD Desferal, but we're going to be talking about a similar variant of it called momentum-based gradient descent, and then we're going to build that up in Adam. So first up, last week we talked about mini-batch gradient descent, where basically what you do is you pass in, say, a batch of 64 samples, and you calculate the gradients for each of those 64 samples, and then the gradient by which you're going to make your updates is going to be the average of those 64 gradients. Now we'll get to something called standard gradient descent with momentum, or momentum-based gradient descent. So essentially, this is a way of tracking how fast you've been going down a slope. So the idea is that if you're going really fast, that means you're going to be somewhat further away from the optimal result, because what you'll typically want is you're just going to be further away from the optimal result. So what you're essentially doing is you have what is called a history. And this history is going to contain past gradients that you've calculated. And the idea is that by taking this history into account, what you want to do is, if you've got a really big average, right? You've been taking lots of gradients and they're it's a very high value for the gradients you've been taking. That means you're far. So you want to take bigger steps. If that history has a small average, that means that you can take smaller steps because you're generally going to be sort of close to the solution. And this is sort of a way to visualize what going through the loss landscape might look like for momentum-based gradient descent versus mini-batch gradient descent. So you can see both start off in the same place where momentum is purple, mini-batch is blue. Then the momentum is going down much, much faster in this landscape because in the process of going down, you see that there's a large change in gradient, the steps are longer, whereas the mini-batch one is going slower. You can see that you're moving, and the mini-batch gradient descent one seems to have gotten stuck in this local minimum. But with the momentum term, the momentum-based gradient descent seems to have escaped, and it ends up in this better local minimum. Yes? Oh, I believe this is MATLAB, but I'm not entirely sure. Yeah. This is more of a visualization than an exact representation, because obviously the loss landscape is not three-dimensional. It's going to be, I don't know, billion-dimensional or more, depending on what your model is. But yeah.
In the previous slide, one thing that we did on the slides is we included kind of how the algorithm actually works. If you can stare at it, you can realize how that here our epsilon is our learning rate, right? That's what we're multiplying our gradient with, which is g. And we have this v term, which is basically the momentum itself, right? And what we're essentially saying is we have this alpha term, which is something really large, 0.9 or 0.99, something really close to 1. And we're basically almost keeping a moving window of averages, an exponential moving window of averages, by basically saying we're taking our previous momentum, multiplying it by a value that's almost 1, but not really 1, and contributing to it or adding to it a bit of our gradients. And by doing so, we're actually accumulating gradients over time because we're basically running this again and again and again. Does that make sense? And you realize you're wait, it's gradient descent. Why is this a plus? It's because we have the minus sign here instead this time. So we have done the minusing in the momentum part, and that's why we use plus here. Does that make sense? Okay, cool.
Mm-hmm. One thing with momentum-based gradient descent that is not here because it's a still image, but momentum-based gradient descent, what you'll find is that it tends to sort of dance around, in the local minimum, whereas this one is going to be more stable. So even though this yields better results, it does have that slight bit of instability that it dances around as it gets closer and closer to the minimum. Okay, next up, we're going to discuss AdaGrad. So far, as we talked about with momentum-based gradient descent, right, this epsilon term, it's been constant for all the parameters, right? All of them have all the parameters, all the weights, all the biases, they have the same learning rate. But that might not necessarily be what you want. So if a parameter has seen lots of change in previous rounds, then what AdaGrad will do is it will give it a lower learning rate. Yeah, that's a typo. And if the parameter hasn't seen much change in previous rounds, AdaGrad will give it a higher learning rate. So the idea here is that what you want, so the idea here is that you want to compensate for changes by making sure that you arrive at places more stably. And so if we look at the equations to sort of demonstrate what's going on here, you can kind of sort of see how they reflect this idea that for each parameter, it's going to have a uniquely optimized learning rate so that it approaches the, so that it navigates loss landscape in a more stable way. Lastly, we have Adam. So Adam is going to sort of combine the insights that we get from momentum-based gradient descent and autograph. So what that's going to do is calculate the mean and the variance of all the gradients that have been calculated for the model. So the mean represents the momentum. And this momentum is going to help the model continue to adjust its weights in the right direction, even as the size of the updates gets smaller. So this is the comparison that we discussed last time between the purple marble and the blue marble. The variance, on the other hand, of the gradients represents the adaptive learning rate that we talked about in the last slide. So here, the variance of the gradient tells you sort of how much the gradient's been changed. Like I guess the variance tells you like the range by which you can expect like the gradient to change on average from round to round. So the idea is that if the parameters have been changing like very rapidly, then you make the learning rate lower. The parameters have been changing very slowly in previous rounds, meaning that the variance of them is sort of lower, then you're gonna get a faster learning rate. So by combining the insights of momentum-based gradient descent, by taking the means of the gradients in the past, and ADAGRAD, where you take the variance of the gradients in the past, you can find local minima much faster by making sure that your parameters are changing in a more organized way by giving them unique learning rates, and also by making sure that you're getting to your desired destination faster and not getting caught in local minimum. Here we are. So now we're going to go into a sort of a short history of convolutional neural networks, followed by a discussion of a few of the architectures at hand.
So, okay. So how did convolutional neural networks become so popular in the first place? We have talked about why we use convolutional neural networks, right? But how do we arrive at the architecture that we have today, right? The idea of we have a convolutional layer, then we maybe have a max pooling, maybe something called batch normalization, and we have a bunch of these stacked together, and then we have some sort of output, right? And how do we get there? And how do models today get so big, so large, and literally speaking, so deep, right? The reason why we call it deep learning is because there are a lot of layers. That is the only reason. And I want to give you a little history of like how we got there in the first place, because it is really enlightening to see how recent deep learning really is. These are some CNN architectures over the years, from all the way from 1998 Linnet 5 to nowadays pretty much sort of kind of the state of the art today, ResNet 50. Because one of the things that people have been saying is computer vision, specifically image classification, is a solved problem. AKA, we have gotten to the point where it is difficult for us to improve it any further in any meaningful way. And I'll show you how by showing you the history that we have here. So it all started out in 1998 with the machine learning scientist Yang LeCun. Who here has heard of that name before? Yang LeCun. Okay, we have like very, very few hands. But he was kind of basically the first person who proposed the idea of the CNN. Not the first person, but the first person to show that, hey, it works really well, right? Because it was only around 10 years ago that they figured out that, hey, we can do back propagation to train neural networks that are more complicated than just logistic regression, where the minimum we can find explicitly, with mathematical formulas. So in 1998, Yang LeCun worked with, I believe, USPS to use CNNs to do hand digit recognition and letter recognition, specifically something called optical character recognition. Can anyone think of why that would be very helpful for USPS back in the days? Why would that be very helpful? Why was that a big deal? Any ideas here? Why would optical character recognition be very... And if you're wondering what that is basically it looks at handwritten digits and it translates it or like converts it into actual typed digital like letters and words. Yes? Exactly. Sort mail by postal code, and perhaps even more importantly, actually not have someone sit there manually typing in the addresses of every single piece of mail that has come through. That's how it worked before. There were hundreds of thousands of these, maybe not hundreds of thousands, but like a lot of different these USPS stations where people's jobs were just look at a scan mail label, type into the computer system what the address was. Tom Scott made a video on this. It's really fascinating. There's only like one in the US currently existing. But before that, that's how all this works. And you can imagine how inefficient that may be,
Jan LeCun worked with USPS to basically say, let's automate basically 95% of that. The 5% of it is really difficult to recognize. We still get that to humans, but the vast majority that we can recognize with computers, let's use the CNN to do so. And it worked. It worked really, really well. And it was one of the first examples of CNNs being used in a large scale. But the next major advancement that we saw in CNN, or the ones that is worthy of for us to talk about today, because we don't have much time, is all the way in 2012. Anyone have a guess what happened in the middle? What happened? It seemed like CNNs were promising, right? Why did it take us all the way to 2012? With hardware, that is one of the reasons. But in fact, during 1998 and 2012, sometime in the middle, around 2000 to 2010, there was this period which a lot of machine learning scientists like to call the deep learning winter, aka a time where not a lot of people were doing deep learning. And the reason will be shown in the AlexNet paper. So I want to talk about what kind of motivated all of this, which is something called ImageNet. So ImageNet is a competition that started around in 2010, where basically it's called ImageNet Large Scale Visual Recognition Challenge, which is an annual competition that started in 2010, where they give you around 1 million training images, and it belongs to 1,000 classes. So these classes included like very specific types of cats, specific road signs, like an apple, pineapple, just like a bunch of like 1,000 general purpose everyday objects. And there were 50K images there for the validation set and 150K for test set, which is not really released to people. And before the AlexNet paper, as you can see here, in 2010 and 2011, both of these methods, they had decent error. So imagine this is like accuracy for the inverse. So like basically here it says they got 28.2% of the image wrong. And specifically, this is what we call top 5 error, which is the model predicts the top 5 most likely class it belongs to. And if any one of them is the correct class, because there's some because there's some classes that are really, really similar, then we count that as that. So in 2010 and 2011, it was 28.2 and then down to 25.8. It was okay. But these methods were basically really, really what we called engineered methods, where they were looking at like patches of images, doing a bunch of like statistic clustering, and they like did a bunch of really big engineering stuff, right? So they weren't methods that we would call today quote unquote elegant, but they worked. Until 2012, when AlexNet came along and absolutely destroyed the competition. The second place was literally 8% behind its classification method. How did it do it? It used the CNN. But you may be like, what? Well, CNNs existed all the way in 1998. Why didn't people do that? It's a really popular paper, by the way. It's been cited over 80,000 times. But its structure looked like this. You have a convolutional neural network, max pooling, normalization, max pool, normalization, max pooling, and some fully connected layers at the end. This looks familiar, right? Like, it seems like what we have looked at. Why didn't people do this before? Why didn't people go, in a way, this deep? So, the reason why we're talking about this network today, because again, it's like basically today's, like default CNN architecture. And the reason why it became so important is because it introduced the ReLU. Does anyone remember what ReLU is from a previous workshop? Okay, so does anyone remember activation functions and what they are? Nonlinearity functions, right? These were functions we put in between layers of networks because we wanted the networks to learn nonlinear results. And you may remember sigmoid, which looks something like this, right? That's sigmoid. And this is 1, this is -1. Oh, actually, sorry. That will be this, and this is 0, right? And I talked about how we had a function called ReLU, which looked like this, right? It just chopped off all the values in 0, and then it kept all the values that are above 0, exactly as it is. This is basically y equals x here, and this is y equals 0. Sorry, x equals 0, right? What AlexNet did is they showed that just by using ReLU, we can make CNN networks deep and still make it work. And the reason is this. After Jan LeCun proposed the CNN, people tried making the CNN deeper. Maybe we can classify more things, classify bigger things, doing like that, classify images that are higher resolution. but they found one issue, which is something called gradient vanishing. Because if you remember, the way we calculate gradients is via the chain rule, right? You start from the ends. Again, we're going to talk more about this next time we talk about backpropagation. And basically chain rule all the way back. You multiply the gradients of like each of the individual functions of our neural network. You just multiply it backwards. However, if we were to use sigmoid or tan H as people later did, which is basically sigmoid but between -1 and 1 instead, when you're near the edges of these activation functions, the gradient is very small. Basically, you can see how the function flattens off, right? The gradient itself actually looks something like this. Right? It really quickly flattens off. And when you have more complex networks, larger networks, it is really easy to have values that have really small gradients. And when you have something that's really small, multiplied by something that's really small, you get something that's even smaller. And it really quickly, exponentially becomes super duper small. And that's the problem. The gradients that we were getting were like close to zero, like almost exactly zero, to the point where we were getting floating point issues, right? The computers were not, like we're starting to get arithmetic issues because it was so small. And because it's so small, the gradients stopped becoming as useful, even if we increase the learning rate. What AlexNet said was, let's use ReLU, which wasn't invented by them, but they said, let's use ReLU. And the reason why we use ReLU is because the gradient of ReLU looks like this, right? The gradient here, y equals x, the gradient is just 1. The gradient here, because it's 0, is just 0. Half of the gradients are still here. And that is enough for us to address a lot of the gradient vanishing problems. It's still there, but it got a lot better. And it made it possible that we can have CNN networks that looks this deep. Does that make sense? And that is why a lot of people say deep learning was popularized by AlexNet. Deep learning was popularized in 2012 because AlexNet showed that we can just use ReLU. And another thing I want to remind you guys is this was before PyTorch. This was before TensorFlow. There was this, PyTorch had a previous version which was written by Facebook right after this or around this time that was in C++. They likely did this paper entirely in C++ or in MATLAB. The reason, it may look simple today, but the reason why the first few years of deep learning, the progress was not very fast was because it was a much higher barrier to entry. It wasn't as easy to write code. Like a lot of these labs, university labs, had their internal like code base where they just used for deep learning. And it was all in like C++ and these languages which is much more quote unquote annoying to do a lot of our operations. PyTorch was a big deal, and like TensorFlow came about a year before PyTorch. They were both really big deals because they really actually democratized machine learning by allowing people to not have to worry about, say, oh, how can I put a tensor on a GPU and write CUDA code? Like it was a lot back in the days. So I want to then move on to 2014, talk about Google Nets and the Inception module. So it is winner of our ImageNet competition 2014 and introduces something called Inception modules, which is still, and the idea is basically we have parallel filters with different sizes to detect varying features. And this is still an idea that is used today in a lot of like image detection and like localization problems, which is why it is also a very important thing. And the motivation comes from the fact that when you have an image, the size of a feature, say the size of a dog's head or the size of their eyes, can vary from image to image, especially in the data set as complex as ImageNet, right? And because of that, we want to see if we can have some way to vary the feature size. And the idea is this. We have some sort of previous layer. So imagine we have like, it was an output of some sort of convolution layer. Then we basically copy this tensor, in this case 4 times, right? The first copy, we send it through a 1x1 convolution. The second copy, we send it through a 3x3 convolution. Third one, a 5x5 convolution. And the fourth one, a 3x3 is just max pulling. Right? Basically, because all these convolutions, they have a stride. You guys remember what stride is, convolutions? Raise your hand if you do, it's okay. We have like a fourth of the people, but basically what stride is how much the filter is moving every single time. So you can imagine how if you have a stride larger than 1, like 2, it will downsample the image by 1 because it's jumping more pixels every time, right? So all these convolutions have strides in themselves, so we use a pooling to also to kind of make sure the output feature size matches the outputs of these convolutions, and we just concatenate them by the channel dimension, right? That's the Inception module. It basically allows us to in parallel, look at the networks at wildly different filter sizes, right? And another thing that's very important is it introduced the idea of one-by-one convolutions, which is something called dimensionality reduction. And the idea is that 5x5 and 3x3 kernels are really expensive if the depth of the input volume is large, right? So like when you're passing, when you input an image, the number of channels is 3, right? It's 3 channels. But then when you feed it through these convolutional operations, they sometimes get expanded to, say, 128 channels, 256 channels, and 512 channels. And the reason is because the way the convolutional operation works is basically, if you say have an input image of 3x32 by 32, which is the size of sidebar center, the data set we're actually be working with today in the code demo, the way the convolutional filter works is if you want an output size of, say, 128 by 32 by 32, you have a filter, and let's say your filter size is 3 by 3. The shape of your total filters is you're going to have 128 by 3 of these filters. And the reason why we have 128 by 3 of these filters is because each of these 3 filters corresponds to each of these input channels, right? And each of these 128 filters correspond to 128 of the output channels. It kind of looks like matrix multiplication by this point, and it basically is. This is matrix multiplication, but on the channel dimension. We're doing basically a dense connection on the channel dimension, and the reason why this is much more efficient than, say, the normal neural network is because with a normal neural network, we're dealing with numbers that are as big as our total number of pixels in the image. But this time, we're only dealing with 3, the total number of channels in the image, which is why it's much more efficient, right? So that's the idea. And if we say, keep in mind that this is kind of like the sizes of our filters, if our kernel size is 1 by 1 or something smaller, it literally makes it so that the number of parameters we have is 1/9 the amount we had before. And that is very, very important. That's one of the main motivations why they did this, right? So you can kind of see how if you have 256 5x5 kernel, that's this many ways. However, if we did something like we have a 256 depth, we feed it to 64 depth with a 1x1 kernel, and we fed it back to 256 with a 5x5 kernel, that's much less weights. Yes, you're losing information, but this idea of the bottleneck, the idea of like we have 256 dimensions, we're sending it to 64, sending it back to 256, and this process we use 1x1. Even though we're losing information in this step, in the grand scheme of convolutions, when we're letting the network learn this connection, it will learn to extract the most important features. So all in all, we've actually managed to basically develop a model with much less weights, which is something that we want because it also means that it is much more computationally cheaper to both train and do inference on. Does that make sense? Okay, any questions so far about all of this? Yes? What do you mean by loss in this case? Oh, like the loss of information? Yeah. So loss of information is like obviously you're like compressing this 256 dimensional of information down to 64 channels, right? So you're definitely losing some information in the process. But as we are learning the network and the network's being trained on this architecture, because that's its own architecture, it will learn so that it will preserve as much information as possible when it's being mapped down to the 64 dimension. Does that make sense? And in this case, if you're asking like what's the loss function, the loss function is just the same thing, right? This is just like some intermediate layer, and the loss function is still just like the classification output, like the cross entropy loss we were talking about last time. Does that make sense? Okay, cool. So yeah, so they call this Inception V2 because I guess they tried Inception before. Well, they call it Inception V2 because it's basically an improved version of that, and then it was in the same paper. But you can kind of see how by breaking up these convolutions into 4 separate chunks, instead of dealing with a 256 channel times 480 channel filter, you're dealing with a 64 times 182, 64 times 96, 256 times 64. Because each of these numbers are much smaller than that concatenated result, it actually ends up saving the total parameters. Okay? That makes sense. You can kind of see how, like just by the virtue of multiplication, we can actually save some parameters that way. Okay, cool. So this worked really well, right? Inception V2 got us to around, if I remember correctly, 6 to 7% in error, which was really good. But it was not human performance yet. In fact, when the ImageNet came out, some like bored grad students in Stanford got a bunch of got a bunch of volunteers together, and basically for a whole weekend they just looked at ImageNet images and tried to classify it themselves, and they found that humans have an accuracy of around 5% in error, right? So 5% seemed like the goal, the thing to beat, and ResNet is what brought us there.
So the same competition that AlexNet participated in 2012, we see ResNet winning it again in 2015. And the way that ResNet did that is with the introduction of something called residual layers. So the idea that we showed before, right, that ReLU gave us the ability to go deep and to still preserve information because we don't have to deal with the vanishing gradients anymore, right? It did that for us. But the problem is, if we end up with too many layers, then we might still make what we might do is make our model too complicated. And so what you can see here is that the 20-layer network seems to be doing better than 56-layer, even though the 56-layer one is deeper. Can anyone think of why this might be the case? So the idea is that if you have a 56-layer neural network, but you only actually need like, I don't know, 25, then you've got these extra layers that are just adding nonlinearities, right? Because as we discussed before, the whole reason we have a nonlinearity function is that we don't want to we want our deeper layers to mean something. So they're going to be adding these nonlinearities and adding curves and like just making the function more complicated. But if you've got more layers than you need, then these added complications are going to lead to worse predictions because you don't actually need them. So the idea that we want is that if our layer is not needed, then we want the output of the layer to be the same as the input of the layer. Because that way, it's like that layer isn't like there at all because the output is the same as the input. So that is something called an identity mapping, where I guess you can see it for the sort of one-dimensional case that you have a number like 2 that gets mapped to 2 by your function, right? But now imagine like taking this from the one-dimensional case that we're showing here to like, I don't know, like a 20, 30 dimensional case, depending on like what your layer size is. So the idea is the same. What we want to go through the excess layer is the same as what came into it. So in practice, what we see through gradient descent is that this identity mapping is actually pretty hard for our networks to learn. But what they are good at doing is going to 0. So what they'll do there is no matter what input they pass in, we can train like the layers pretty effectively to just go to 0 and have that be the output that they spit out. So does anyone have any ideas on how we can use this property that we can't learn the identity mapping really well, but we can go to 0 really well? Does anyone have an idea on how we can sort of use this property of going to 0 to sort of simulate the identity mapping? And this is like a bit of a leap, so I wouldn't blame you if you can't think of it, but just like give it a thought for like a couple seconds. So the idea is what is called the residual connection, or also known as a skip connection. And this is sort of a diagram of what's going on here. And we're going to go into like the nuts and bolts of this diagram in more detail. But this is sort of an underlying picture by which we can get back the identity transformation, even though we have like an extra layer that's adding this non-linearity. So as we discussed last week, the traditional structure of a feed-forward neural network, right, is that you have a hidden layer. In this case, we'll call it layer 1. You multiply it by some weight matrix, and then you add a bias, and then you put it to a non-linearity function, and that's your second hidden. Does everyone remember that from last week? Okay. Now the problem is, again, as we said before, we don't actually want hidden layer 2 to be there at all, right? So we want to make it, we don't want hidden layer 1 to be there, right? We want to just sort of pass in the same thing that we got back before, but we can't do that because of this non-linearity function. And that's where the skip connection comes in, and that's this added term right here, the input layer. So the idea is that if our hidden layer 1 is actually not that useful and we don't want it to be there, what we'll do with this is that you learn how to set this equal to 0. Because as we stated before, our models are really good at figuring out how to send the outcomes of layers to 0. So if this entire term starts going to 0, then what we end up with is that our second hidden layer is equal to our input layer. And that's good. That's what we want, because that means hidden layer 1 effectively has no effect. Yeah.
Like, what's the point of this if we don't want hidden layer 1? Can't we just redesign the network so that we have one hidden layer?
The problem with that is we don't know if we want hidden layer 1 or not. Because if we have, say, 56 layers, right? Maybe we want 25 of them. But how do we know that we want 25 ahead of time? Right? Because this 25 is just some sort of abstract number that I pulled out of thin air. It's some optimum, but we don't know what that optimum is. So the idea is that some of these hidden layers are needed, some of them are not, but we don't know ahead of time which ones are and which ones aren't.
So
Yeah, exactly. Whatever layers we want, they're not going to go to 0 because we want them to have an effect. And whatever layers we don't want, they are going to be set to 0 because models are good at knowing when they need to do that, and we'll end up with just a simple identity. Any more questions? Okay. Perfect. So now if we look at this diagram again, hopefully it makes a little bit more sense. Right? You have your input layer, you pass through the weights, you pass it through the nonlinearity function, that gets to your first hidden layer, then you pass it again through really, but you also add your identity. So that way, if needed, this whole thing can zero out and you literally just Okay. And then there's another technique that we'd use called batch normalization, where what we'll do is we'll take the outcome of a layer, and the numbers in that layer might be wildly different from each other. But what we'll do is we'll normalize them so that they have a mean of 0 across all the numbers in the layer and a unit variance of 1. So has anyone here taken a stats class? So if you've taken a stats class, effectively what we're doing is we're calculating the z-scores for all the numbers in our layer. And we're like replacing them with their z-scores because that way they're normalized. And so they don't like have widely varying ranges, but we've sort of contained them a little bit.
Well, one thing I want to mention is one of the reasons why, again, ResNet is possible, because remember the whole vanishing gradient problem? The fact that we have the identity also helps with that. Because what the identity means is the gradient passes through. Remember? Because if we have the function y equals x, what's the derivative? Just 1, right? Which means when we're multiplying this derivative in our chain rule all the way back, multiplying by 1 just keeps the same thing. Maybe the gradient is not solved a lot of our gradient vanishing problem. And ResNet also popularized the batch normalization, which further helped with the gradient vanishing problem because it tries to normalize the magnitude of our intermediate feature every single layer, or a lot of them. And it is normalized across the channel dimension. Sorry, it is normalized across the batch dimension. So imagine if you say have a batch, you put in a batch of 128 images. Our intermediate features will all have a batch of 128 because it's the intermediate features of each of the images have to fit together, right? It basically says, all right, those 128 images, we're like assuming it is the representation of the means and standard deviations of the entire data set. So let's kind of normalize our features across that, and that's basically what it is doing. Batch normalization today does something a little bit more. This one they did a little bit more, which is instead of just keeping that like while training, it keeps track of that. It gets its mean and standard deviation from the actual input itself. But this is a little problematic when we're doing input, right? When we're actually testing the network, because when we're testing the network, we don't want features. We don't want to have 128 images at a time. Especially if they were testing the computation of like these 128 images happens to all be blurred. You can see how the distribution of those intermediate features may be skewed compared to our training set. So what we do is while we're training, we also a moving average, a moving mean, and moving average over mean and variance of these terms. And when we're doing inference, we use these terms instead of our inputs' mean and variance, just so that when we're doing inference, how putting in one image versus putting in two images, putting in image A and image B versus putting in image A and image C does not change our results of like say what image A would be, because that will affect the distribution. If we were to say keep track of our mean and standard deviation while we're training. Does that make sense? Okay, cool.
So and I want to emphasize like next slide. Oh yeah, another quick thing with training ResNets, they actually use gradient descent with something called Nesterov momentum, which we'll talk about in like 1 or 2 workshops because it's just like basically fancy momentum. But one notable thing that they do is they start out with a learning rate of 0.1, which is really large. After it plateaus, they drop it to 0.01, and then after it plateaus, they drop it to 0.001. We find that really bizarre. Like, why are we dropping learning rates by tenfold every single time? And the motivation behind this is that this is actually a technique that's been known for a little while up to this point. But the reason for doing this is if we have a really, really big learning rate, our model in our loss landscape is kind of jumping around. Right? The gradient that it's taking is really large. So if we give it, say, 10,000 iterations, this is 60,000 iterations in total. If we give it 10,000 iterations of it just jumping around, it is going to eventually end up at a point where if there is a really good global minimum, it's going to be a very shallow minimum. Because if you have a really sharp minimum, what will happen is it will just jump straight through it, right? So after we have honed in to a rough location over a really nice global minimum, we drop the learning rate, and we do the same thing, but at a much smaller scale. And we do it again. We drop the learning rate, and we do it at a much smaller scale. So hopefully at the end, we're going to reach a global minimum that's not just a very sharp minimum, but a really flat one. And you can imagine how really flat minimum means that the model is not overfitting. Because if the model is overfitting, that means it is really sensitive to the original, to the image you put in. If you just strip the image, say, from red to blue, huge dip it a little bit, it makes come with complete results. If the minimum is very, very flat, it means the model is very safe. It is much less resistant to if the input is a little bit different than the training data set. Does that make sense? So that's why we use training data. And I can't emphasize enough how important the ResNet paper is. It currently has 180,000 citations. It is the most cited paper out of the entire history of academia. That is how popular this paper is by Kai Ho, who I think now is a professor at MIT. This paper is so unbelievably important. Almost every single deep learning paper after it use some sort of ResNet mapping, use some sort of identity mapping. ChatGPT with transformers. Transformer has identity mappings built in. Any sort of computer vision that you have seen nowadays. Stable diffusion. They all use the identity because it not only helps training, it's just it is so good, right? It is such a simple idea, yet it works so well. So that's why it has 180,000 citations, because almost every single deep learning paper that's ever came out after ResNet will probably cite the ResNet. Does that make sense? Okay. Cool. Let's continue. Yeah.
Oh, real quick on the note about the lost landscape. Can anyone explain why it is that if you just have a very shallow minimum that it would be sort of sensitive to changes in the test set? Yeah, totally sure. Okay, so just to clarify that point slightly, is that whatever lost landscape we end up with, right? Say I'll do it in 1D version so that it's simple. That, for instance, and this is what our landscape looks like. This line right here. What we'll see, right, is that this lost landscape is defined entirely by our test data set. So what we're hoping, training data set. So what we're hoping is that the training data set is reflective of our test data set. But of course, it's not going to be exactly reflective. It's going to have so many idiosyncrasies, the means might be something different. And so because of that, if we're too focused on these little sharp deviations that arise in the lost landscape from our training data set, where those patterns might not exist in the test data set or in the overall data set at large. And so what we want to make sure is that what our training data has is reflective of things overall. And the way we do that is we make sure that we don't have little sharp changes, but we have a nice shallow area for the minimum, so that we know that this shallow area is actually from the overall data set because it's not just a little blip.
Yeah, so we're also going to talk a little bit about computer vision problem spaces. So these are just some of the problems that we deal with when we're talking about computer vision. So classification, detection, and segmentation. So the basic idea here is that when we're looking at an image and there might be multiple cars, but do we classify each one as a car, or do we do car 1, car 2, so on and so forth? And also, how big is it? Yada yada yada. Those are the kinds of questions that CV problem spaces attempt to answer. So classification is simply, what is it? Is it a dog, cat, car, whatever it may be? And obviously we have the label. We also have the detection and localization. So where is the object in the image? Is it in the corner? Is it in the center? This is, so with detection and localization, that's what we do. But also the other important thing is segmentation. Which pixels does each object occupy? Is this pixel part of the dog or not? As we see here, this section right here is the dog, but this is not. So as I alluded to earlier, there's a difference between regular semantic segmentation and instant segmentation. So regular is just saying, oh yeah, this is also this, so on and so forth. But instant segmentation tells us also, it distinguishes between multiple instances of the same class. So here we have puffin 1, 2, and 3, even though in regular semantic segmentation, they're all puffins. Any questions about that? No? Okay. Hmm? Okay, do you mean, just to make sure I understand, so you're saying like, how did we choose one to be one and, okay. Yeah, in this case, it seems like the most obvious explanation for this one is probably just left to right. But there are many ways you can do that. There's no reason that like this has to be the way. Any other questions? Okay. All right, so now we're going to go into a quick note on ethics. So let's talk about the environment real quick. So AI and ML, it's a double-edged sword with the environment, right? So on one hand, it can be used to help balance supply and demand needs, and which optimizes energy usage. So if you apply it to direct power to certain places, you can help optimize and basically only provide the energy that you need to, which is good. And then also NASA has been using AI to monitor changes in landmass and pollution. So there are all sorts of applications that AI can use, where AI can be used in terms of environmental. But there is a downside, which is training is computationally expensive. And obviously training a single AI system requires a lot of energy. And as we see here, it can emit a lot of tons of CO2, which is not great. And obviously, it's the use of AI produces around the same CO2 emissions as the aviation industry, which I think is like, what is it, like 2% of global emissions or something like that? I don't know what the exact number, but 2% and then like two more percent. It's a pretty big number. So it's definitely so it's like I said, there are applications that can help the environment, but AI itself, it's not the most environmentally friendly. So now we're going to go into the guided project, and you take it away.
This link here, it's not add link, but like it's the cluster. If you log into cluster, you should be able to see it. I'm just gonna come out here. Yep, there we go. So you're gonna see. So again, if you go into the cluster, you can just click on the link which has today's demo. And basically, this is our guided project that's going to last probably for the next 3 workshops, where just to give you a little overview of what we're planning to do. Today, we're going to be going through the first part of this notebook, which is how do you build your own CNN network, right? How do you work with PyTorch? How do you look at different dimensions of your tensors and whatnot to be able to build a classification network that is going to output the correct size. That's not going to give you any math errors. Part 2
next week, we're going to talk about the training. How do we actually train a network? How do we do that in PyTorch? And I'm also going to talk about how PyTorch works, backpropagation, all that stuff. And the third workshop from today, so the in 2 workshops, we're going to have a session where basically you get to train out your own network, tune the different type of parameters, play with different network architectures, and we're going to have a little mini competition of see who can get the highest accuracy outside of the data set. Does that make sense? All right, awesome.
We might have a prize at the end, so you guys should stay tuned for that. So right now we're going to give you guys a brief overview of PyTorch. PyTorch is one of the most critical machine learning libraries we have today. It's a machine learning library for Python, and it's built around the idea of a tensor and the tensor library, right? So a tensor is essentially a multidimensional matrix. And what makes tensors so effective is that we can feed these tensors directly into the GPU, right? Which is a graphic processing unit. And this makes a lot of the calculations much more effective. For example, matrix multiplication and so on, it makes it more effective. So essentially, PyTorch is just one big matrix library, one big efficient matrix library. In addition to that, another extremely important aspect of PyTorch is its autograd feature, or its automatic differentiation feature. So what that helps us in doing is it helps us calculate the gradient of our structure. So suppose, for example, we have a neural network, right? Can you guys see this, by the way? Suppose we have a neural network, right? And it has like multiple layers and so on. Right? And it just goes on, it has multiple layers. And then we want to calculate, let's say, right? So the derivative of the weight, right? The derivative of the ear and the derivative of the weight. So we want to calculate this derivative to decrease the cost function in that direction of the steepest descent, right? To calculate this derivative, it's very difficult if we just look at the function as a whole, because it'd be this extremely gigantic function that we would need to calculate. But if we calculate each step of the way, applying local gradients and using the chain rule, you guys know what the chain rule is, right? You guys have seen this in class? Okay, that's good. So we essentially take the derivative tree of this neural network and we apply the local gradients, and we just multiply the local gradients, right? For example, suppose, right, the first function we have, here, is k, right? So we'll take that, then, right. Take that, then suppose the second function we have is L, right? And so on, until finally, we get to, suppose one of the functions we have is, right, z, until finally we get into the smallest function we can potentially find, and then we calculate the derivative with respect to the weight. So we just need to multiply these local gradients to get the total gradient at the end. So this is much more efficient than doing it the opposite way. A downside is we need to have the gradient tree for the calculations. So we need the gradient tree of the neural network to be stored so that we can optimize. There are techniques that don't use this. For example, there's something called forward automatic differentiation, which uses raw numbers to calculate this. It's a fascinating area of research, but for now, we usually have to store the gradient tree. So let's start with the coding demo. These are the libraries that we need. If you guys use Google Colab, by the way, and if you guys check on the asset cluster, you don't need to actually like download the libraries and set up your environments. But if you're doing this locally, you do. So if anyone needs help setting this up, let us know. We'll help you guys out. Anyways, yeah, so this is us setting up libraries. Does anyone have any questions on what the libraries are before we get into that? Nope.
One quick thing. Just so that we're not modifying the original file, let's make a copy of it. So copy and drive. We have access to it, so this is not an issue, but if you guys notice, we have to do that. And I will also just real quickly make a slide more visible on, because the lights are on, so there we go. Maybe it's a little bit better. Okay. There we go.
Okay, good. This is clear. So let's go to the next part, right? And right here, we're loading the device, right? Essentially what the device is what we're asking is, do we have a GPU? If we do, use the GPU. If we don't, oh, sorry. Yeah, we have to rerun the first. I was like, wait, what's going on? Okay. Give it a sec. Essentially, what this is saying is, if we have a GPU, use the GPU. If not, use the CPU, right? Now, hopefully, we have the GPU. In this case, we do because Google Colab gives you guys a GPU. And this is much faster than using normal CPU because GPUs are optimized for parallel computations, matrix computations, and so on. That's one of the reasons why they're made. So yeah. And right now, hold on. I guess it's not available for now. We'll come back to it. What happened?
So this is happening so you can change the runtime?
Yeah. Here. Yeah.
Okay.
Yeah.
Thank you so much.
Wait. Yeah. P for GPU, I think is perfect.
Reload it. Sorry, guys. Take a little bit. So now we're running on a GPU, the Tesla T4, and then next we're going to download the dataset, right? So the CIFAR 10 dataset is already available for PyTorch automatically. You can download it from a server online, and we can download the training and the test dataset separately. This is just telling you, that it's not the training dataset. And what this does specifically is it takes the whole dataset and it turns it into a tensor. You guys remember PyTorch, the basic building block of PyTorch is a tensor. Yeah, let's run that. It's going to download it. Then while it's doing that, let's go to the next cell. These are just the loaders of the data, right? So before, when we were talking about loading data, we said that we use mini batch gradient descent when handling training, right? And so the batches of this training are 120. So there are 128 images in a batch. So that's what that's saying. And this is essentially the training data set. This is the test data. And this is what we're going to be to test the data, and this is what we're going to do while training. Right here, we don't optimize. Right here, we do optimize. And helpful just means that it's random. Right? So randomization helps generalize better because now you don't control what data you feed into your neural network. So yeah, so we got the files. Now we're gonna. So does anyone have any questions until here? Nope. Okay. So now we're gonna give you guys a glimpse of what the yeah. So now we're gonna give you a glimpse of the image data set. So right here, the number of data points you have is 50,000. This is for the training data set. The testing is around 10,000 altogether. There's 60,000 data instances. In the root location, this is just telling you where it is in the server, and this is the so log it is accurate. And the torch size is the size of the tensor. Right? So the images are 32 by 32, and they have 3 input channels for the RGB value. So yeah.
Oh, one thing I want to know, which is something really annoying that only PyTorch does. You realize this image is 32 by 32, and 3 stands for RGB. Why is 3 in front? If you were to say unpack this image, like open this image, NumPy, any single other, even TensorFlow, any single other package for turning images into matrices, it'll say 32 by 32 by 3. However, PyTorch loves to do this thing where it puts the channel first instead of the channel last. And that is a very big distinction sometimes you have to keep in mind because like in our code, you may see something like, dot move axis. That's basically what we're doing because we are converting between normal NumPy images to say display the image in matplotlib versus trying to do things in PyTorch. You will have to move this channel around. So that's just something you have to keep in mind. And the reason why I think PyTorch does this is because when you're doing like filters and like all that stuff with CNNs, you're dealing with the channel in the front, but you're also dealing with another channel here. Like you're doing matrix multiplication in these dimensions. And you're not touching these dimensions. So having the channel in the front a lot of times actually helps with a lot of the efficiency and easily understandability of like the PyTorch like matrix multiplication and CNN like within. However, if you see, this is why our channel is in the front end, not in the back end. What I want you to keep in mind, because if you say just convert this directly to NumPy and try to show it with matplotlib, it's not going to work, because matplotlib will be like, what the hell is a 3x32 image with 32 channels? It's not going to work. So make sure to move the axis back here before you convert it back to NumPy, or do it in NumPy. Just like make sure to move back the axis. Got that? Okay.
Is there for efficiency?
It's partly for efficiency, but partly when you're in the thick of like trying to figure out like, oh, what's my channel? Because like you don't really care about image size sometimes. Like having it in front is much better. There's probably more official reason. I never bothered to look it up myself, but
Yeah, it might have something to do while you're like doing matrix multiplication. You guys are like cache optimization and so on, because you're looping through the inner. You're looping through that. If you guys taken CS33, like it's more cache. Cache friendly, exactly.
spatial locality.
Spatial locality, exactly. So that's one reason why this is so helpful.
Basically, when we're doing these operations, we're doing it on a channel by channel basis, right? We're asking a bunch of these 32 by 32 stuff, and then eventually we'll go to the next channel. We're doing a bunch of these stuff in the 32 by 32 level. We want to make it so that the things that we're accessing at once are closer together in memory. So we have this 3 here. We're constantly skipping 3 bits, like 3 in memory, 3 in memory, 3 in memory, which is not very efficient. But we have bunch all these together and kind of group them by their channels. We have a much better spatial locality. Again, you learn more about this. Just probably my favorite lower than CS class.
Yeah, he's an excellent LA, by the way. If you guys had him, the best. Yeah. So yeah, that's what the permute does. By the way, it just like it just switches the channel, the shape of the image. So yeah, that's what the permute does. Now this is one of the images. You guys might be wondering, what is this? Is this a car, I think? I might be wrong. I think it's what wrong with that. Yeah, this is the. Yeah. If you get it wrong, it's fine. But anyway, by 32 pixels, you can feel it a very difficult task, because first it's pretty blurry, right? And second, there are 10 different outputs that you're classifying from, right? So it's actually quite different. Like how can you tell a train from a dog, for example, right? In this level, it's quite a difficult task. And so let's go to the next step, which is building the model. Right. So the model class that we have, it's the CNN class, and this is basically a subclass of the NN module class, which is the class that essentially controls all aspects of a layer and a module, and the parameters of the module and so on. So that's the base class, and we're making a subclass of it, right? So that's why we have the super array. We're just inheriting all the attributes and methods of the super class, which is the NN module class, and that's explained there. And these are the layers of our neural network. Within the CNN module class, we define the layers of our neural network. So the first layer is a convolutional layer. It takes in 3 input channels and it outputs 32 feature amounts, right? And the kernel size is 3 by 3, and the padding is 1, and the stride is 2. Now, just to like get into the room a little bit, because the stride is 2, right? Given and just ignore everything about the kernel for just for a moment. What do you think the output image will have? Feature will have in terms of dimension. What do you guys think the reduction is going to be? Because the stride length is 2. Like let's say for example, is it going to be a half? Is it going to be a fourth? Is it going to be an eighth? Like what do you guys think it's going to be? Because the stride length is 2. Yes. What? Suppose, for example, you do have a 16 by 16 image, and the kernel has a stride length of 2. How do you guys think the image dimension is going to be reduced? 1/4? You're close. Like 1/2.
Well, total number of pixels would be 1/4.
Well,
Because we're doing 1/2 of each height and width. Oh, height and width, respectively, total half of width.
Yeah, so I was right. He's right, guys. Thank you for that. Appreciate it. So yeah, so it is reduced by drastic amount, and you can imagine that when you do reduce it, it becomes much easier for computation. So yeah, that's what the convolutional layer does. And this is the batch norm layer. This is the batch norm for 2D. There's batch norm for 1D when you have a linear layer. In this case, batch norm for 2D, and it's just taking the 32 big feature, and it's having a dashboard on that. So this is just a ReLU activation that we're going to apply for this layer, and this. Can you guys see it? This right here is the dropout. So what the dropout essentially does is it takes your activations, it takes your weights, and this percentage of them, in this case it's like 10% of your weights are going to be 0. So you're not going to use those weights. It does this randomly, so you're not going to use those weights during training. And the reason it does this is to better find the minima and generalize for the data. Because at certain times when you reach a suboptimal, it might be very hard to move around. But if you sort of like handicap yourself, you might look for other ways of approaching the data, and you might start to gain other features of the data, which is what you need for generalization. So this is just the second convolutional layer. Yeah. And in this case, it's 5% compared to 10%. This is just the third convolutional layer. And you guys see we have a pattern, right? Wait. I forgot to mention the max pooling layer. So right there, we have the max pool layer, which as we talked about yesterday, you have a cluster of your image, of your pixel, and you just take the maximum of those pixels. And then in this case, it's 2 by 2. So we're reducing it by 2 again.
Oh, one thing, right? So what we have done here is we did a stride situation, and then we did a max pool. We're doing this kind of as a demonstration. Usually, nowadays, people won't put a stride and then immediately follow with a max pool. People do one or the other, right? They either do stride or they do max pool. However, nowadays, we don't really see max pool anymore. We see some average pooling, which we'll talk about next week. But people just use stride. Why do you think that's the reason? Why do we prefer to use this pixel skipping method or stride skipping method to downsample our image versus don't do the pixel skipping and then just do a max pool? Why would we want to do one over the other? There's actually several reasons. There really isn't an incorrect answer. Any ideas on why we're doing this? Why one over the other? Yes. Yeah, kind of. The central idea is that when you're doing this convolution striding, it is a downsampling operation that's learned. We're letting the filters learn how it can formulate itself, remember nudging the weights around, right? So that it can almost perform both downsampling and also feature extraction. However, if we leave the job to max pool, convolutions can do slightly less because the downsampling operation is always the same. It's something predetermined, it's something that we cannot understand. Right? So that's why people nowadays tend to use max pooling more than people nowadays tend to use strides more than max pooling. And another thing is, if you think about it, when we're doing this pixel skipping, we're actually reducing the total number of filter calculations, filter dot products by 4. Think about it, right? Before, we are moving through every single one like this, but we're skipping one every single time in this dimension, and also skipping one in every vertical dimension. We have reduced it by 4, right? We're halving the total number of operations we're doing each time. And by doing so, we have just made the entire network much faster. However, there is one advantage with max pooling, which is it is spatially invariant to small movements. And the way to think about it is if you have a really big value here, and you say move this entire feature map right by 1, your max pooling is still going to give the same value, which means it is much more, max pooling, theoretically speaking, is less sensitive to the input image moving around, especially if your input image doesn't have a lot of variation to it, or your training data set doesn't have a lot of variation. It tries to preserve that sort of spatial invariance that CNNs tries to preserve in the first place. But in testing, because a lot of our data is really large and diverse nowadays, that's not really a problem, and that's why we stick with strides instead. Does that make sense? Okay, just a little convention of what we do nowadays with a lot of computer vision problems.
Thank you, Jordan. And to continue with the next layer, we have a flatten layer, which essentially takes your tensor and it flattens it out to input into the feed-forward layer right here. And we flatten the tensor and we do it to a linear layer. And then this linear layer has an activation layer function. And we finally get to our final linear layer, which takes it 128 the alpha 10. So, and which is the number of classifications you want to have. Does anyone have any questions on this? Oh, sorry.
Yes.
Sorry. Does anyone have any questions on this? Yeah, let's go on. And this is your forward. All that this function does is it takes an input and it puts it in each step of your layer and it outputs it out. That's it. And after which you start optimizing. So that's the forward propagation function. And every module class should have a forward function because, you know, why else would you make a module class if you're not gonna? And right here, we're just loading our model, and we're saying we're using the device for our model. So you guys remember what the device was from before? It's just telling us, are we using a CPU or a GPU? In this case, we're using a GPU. This is our model right here. You can see. And then we define our criterion. Our criterion is essentially what loss function are we using, right? What year function are we using? In this case, we're using cross entropy loss, which is really good for multi-classification problems. We can also use MSE, but mean squared error. But in this case, I think it's best if we use cross entropy loss. And then this is just defining the ADAM optimizer. For the ADAM optimizer, when you do define an optimizer, you have to give it the parameters that it's optimizing, because the optimizer controls the movement of the gradient, the movement of the weight, right? So to do this, you have to actually give it the weights that it's going to control the movement of. And you have to give it a learning rate, and the weight decay factor is 10. Yep, this is the weight decay factor. Now, if you guys are wondering what the weight decay factor is, it basically serves as a L2 normalization technique. So what it does is it makes it so that the weights never get too big, right? So it basically tugs the weight vector towards the origin. It's like, yeah, I can explain the math after this if you guys want, but it essentially serves as sort of like a bottleneck for the weights so that they don't get too big, and that if there are weights that are not needed, they get zeroed out. So that's the weight decay factor. And yeah, this is a training function. So we enumerate over our train loader. We take an iteration of our train loader, and then we split it into the inputs and labels. One important thing to note again is that PyTorch works in batches, right? So we don't input one by one, we input in terms of batches. In this case, we have 128 images. That's how we input. And so we have our inputs and we have our labels, which are the outputs for it. So for example, one image might be an image of a frog and the label is frog, So that's how it works. And right here, we're just loading again our tensors to the device, the GPU in this case. And then this is where we call on our model output. So model bracket input just calls the forward function from before, right? So model input just calls the forward function of model, and then that's what the output is. Yeah. And then the loss just calculates the loss between the output and the label. And then that's it. That's the loss right there. And then loss backward, that's our gradient descent algorithm. So we've already created our gradient tree. Now we're just going backwards in our gradient tree, concatenating the derivatives and just multiplying them out. So that's what loss.backward does. And optimizer.step, once we've gotten our gradients, we need to step our weights in the right direction, right? So that's where we update our weights. And then after which we zero out the gradients so that we don't use the gradients from before. This is a very, very critical step. A lot of people forget this and they wonder why their gradients their weights are exploding. This is usually why. So yeah.
Oh, and also one thing to note is like we see optimizer.step, optimizer.zeroGrad, as we mentioned at the start of today. The different optimizers are going to do this differently, which is why the choice of optimizer is this step right here, the backprop of the optimizer.
Okay, this is the testing, right? And just from viewing this, what do you guys think is very different from the training function? What do you guys think? What are we missing? I guess not missing, but what's not there? What's not there? Guys. But specifically, in this case, what we don't have is the optimization, or we're not optimizing anything. All we're doing is we're calculating, we take the model input, we take the output, and we take the max of the output. Because before, you guys remember when we talked about how the max of a neural network, in this case, is the probability of that image being a certain classification. So we take that probability and we find the maximum of that probability, and that's our prediction. If our prediction is equal to the label at that point, right, that's true, one. If it's not, that's false, right? So we lost. So there's an issue. And we sum this, all together, and then we divide by the number of iterations, and then we multiply by 100. There we have the percentage accuracy of our training. So do you guys have any questions on this? Okay. And right here, don't worry about this too much. All that this is doing is it's giving us like the final testing data, and it's so that you guys can see what's happening in the testing. You'll see why this is important. Test training. And then the number of epochs we have for now is 2. What an epoch is essentially one go through of the whole training data set. So one epoch in this case is 50,000 images. So two epochs, you're going through the data set twice. And the reason we made it 2 is because it's pretty slow. We don't have very fast GPUs, and so we have to do it at 2 for now. Let's see. Dang, I should have started this before. Yeah, we lost it first. So this is the estimation for the testing data set. The loss of the first accuracy is around 57.89. Can you guys guess what image this is? What is this? Can you guys guess?
You squint your eyes, then you can sort of see it a little bit better.
Because I have no idea.
Cross your eyes and like this really blurry vision.
Yeah, it's tough. It's tough. I'm not gonna lie. And this right here, it's a deer, and the model classified it correctly. It said it's a deer, right? And this right here is a ship. The model classified it correctly. It said it's a plane, but it's actually a bird. And honestly, anyone would say, this is not. And this right here, it's a deer, but the model classified it as a horse. We're starting to see that the model is actually making sort of logical decisions, right? So, yeah. So these are. And finally, at our last epoch, we have an accuracy of around 58.35, and that's not bad for 2 epochs. It increases as we go along. It stagnates after a little while. But yeah, that's the final accuracy. And these are the estimates we have. Right here, we have a frog. It's actually a plain horse, but a dog, and so on. Do you guys have any questions on this? Any questions? Okay. And right here, we're just printing the number of parameters that we have. You see that?
If you know what dropout is, that's something we didn't talk about this time, but I mean, we'll talk about this in the future a bit. Like, on either the next workshop or the workshop for that, we have a full session on how to improve your machine learning model training, where we're going to be talking about dropout and a lot of other methods to try to prevent overfitting, such as augmenting data set and stuff.
We have over 100,000 founders, which is kind of big, right? But when we compare it to actual neural networks today, they have millions upon millions of parameters. So this is kind of nothing, but it's still impressive, when you think about the magnitude and the scale. And this is how you save the model, right? Because once you have a model, you want to save it so that you can use it again, right? And so, you just save it as model.path. Model.pt. Yeah. So right there, it's saved, as you can see. And then let's reloaded the model from model.path rather than our previously trained model. So, yep, it's the same thing. Let's test it again, just to see if it works. Yeah. And you see, usually the testing happens much quicker. Can you guys sort of guess one reason why the testing is usually quicker than the training? And it's not usually, it's all the time. Every single time it's quicker than the training. Yeah? What? Yep. That might be one reason. And do you guys have another reason? That's good. Yeah. Yep. It might be that for the testing you might have less. So you might go through it less. Yep. Those are good points. And one other pretty critical thing is that for testing, you don't optimize. You don't do any optimizations, right? So because you don't do any optimizations, you don't have to make the gradients, you don't have to make all that. And so it's much quicker because you don't have to account for that anymore. Yeah. And these are the things. And so I'm going to download pre-trained weights that we trained before from my GitHub right here. Yeah, it has downloaded. And these are pre-trained weights that we've already trained before that have a little bit higher accuracy, around 72% accuracy. So 7 out of the 10 images, they correctly estimate.
By the way, for the
Go ahead.
another third line version of the bullet doing the same bracket, it's like model.phw. It said indexes.
It didn't, maybe because did you download it? Yeah. Wait,
You like a WGET, a WGET thing.
Okay.
Yep.
Yeah.
Click on the WGET. All this is doing is going to my GitHub and it's downloading the model weight in there. So that's all that is doing.
So you pre-train it for you, but next time you get to train this. Yeah. Out of the
Okay.
time. So it's usually training one of these takes like 30 minutes, 1 hour, maybe a little bit longer. So yeah.
And in this case, let's evaluate this. So the accuracy is supposed to be 72. Yeah. So it's around 71.84. This is better. This is like around 20 minutes of training. And we increased the accuracy by a good amount. And as you can see, most of the examples are trained correctly. 7 out of the 10 examples. And we can improve on this drastically. We can do a lot of techniques to improve our neural network. We can add residual layers. We can transform the images so that we can get a more generalized estimations and so on. We can do a lot. Yeah. And if you guys want to work on this, it's on the asset cluster. Feel free. And if you guys have any questions, feel free to ask us. Also, thank you so much for your comments. We really appreciate them and the questions.
One really quick thing, I want to see a show of hands. Next week, because next week is midterms week, who here has a midterm on Thursday of next week? Raise your hands. Because we have a few hands. Since you guys have a midterm on Thursday, would you guys come to the session if we were to have a session this week? Okay, we're seeing some nods. Okay, because midterms, I know it's midterms week, I know everyone's busy. This is how we're going to do this. Next week, we're going to basically make this sort of like semi-work session where you're going to just sit here and train your own neural networks. Our office will want to help you. But at the same time, we will also be giving like a short, like 20-minute presentation on how to improve your machine learning model training, where we give a lot of tips on how we can make your models better. And the week after that, week 6, Wednesday, we're going to be talking about a much more important topic, which is PyTorch backpropagation, where we really go through the training loop and go through how exactly that loop works, why we have each output that we do. And at the end, we'll have a little competition on see who can train the model the best. And a little preview the weeks after that. Week 7, we're going to be talking about transformers, on RNNs, and just a lot of techniques that we use to do time series data or sequential data.
And week 8, we're going to be talking about a lot of more modern computer vision techniques, specifically a lot of generative vision, how stable diffusion works, how generative episode networks work, and things like that. So hope to see you guys next week. If you can't make it next week because of a midterm, that's totally fine. But week 6 is definitely the very important one that really lets you learn how to train your models in PyTorch. And once again, the attendance code is over here. It's Jackson, but in CNN. Go in our back. And it's funny. We'll see you next week or the week after.